begin with the Islamic greeting. Assalamualaikum warahmatullahi ta'ala wabarakatuh. May God give peace and hidayah to all of you. Selamat pagi and good morning. Right, in the last lectures, right, we already discussed the new topics on conduction heat transfer in solid. Statistically, we look at the cases where temperature is only varies in time, and the body is, we can say that is approach to the thermodynamic equilibrium, or you can say that the body is in quasi thermodynamic equilibrium. And we are looking in the cases where the heat transfer system is exposed to the fluid, and the fluid is like a large temperature reservoir. When we have a body at different temperature, it will not change the fluid temperature. Right. In that introduction session, we have looked at new concepts that you never heard before, and some of them you have heard before. One of them is the characteristic length, right? And I already gave you a quiz with regard to this concept. So why we need to have this characteristic length? This characteristic length is been used to determine the criteria at which our system can be considered as a lump system. Lump system means the body is approaching thermodynamic equilibrium instantaneously. And then we look at the, but this criteria does not necessarily been used in to determine the temperature history for the body, for the heat transfer system. Right. And when we talk about temperature history, we want to see, this is another concept where we want to see the changes of temperature with time. That's what it's called history, right? So when I say the adjective for history, time history, means that we want to know about the changes of temperature with time. If we are working on senses, we are looking at the response of the senses. We want to know at how long it takes for the senses to record the temperature of the body that attached to it, right? So when we use, for example, thermocouple or thermometer, if you are using a mercury thermometer, of course, when we place thermometer inside a hot water, for example, we have to sometimes, like myself, I like to watch the mercury rising, right? If it's the fluid temperature is higher than the thermometer, we want to see that the rising of mercury until it reach to the final temperature, where the temperature does not change. If the thermal inertia is so high, it will take long time, right, to reach to its final temperature. So that is the response, right, for that thermometer. And then we look at the Fourier number, right? Fourier number is a non-dimensional temperatures in non-dimensional time. And we have a Biot number, is another non-dimensional parameters, just like a Reynolds number. And then we want to know what is the temperature difference, non-dimensional temperature differences, which are given by the symbol theta, right? So those are the concepts that you learn in the our earlier lecture on this topic. Right. So I might not mention everything in this review session, but we're going to look at those I forgot when we do a sample of calculations. So we're going to use the example in the books, right? So every time that you do some revision, we can use the example, and then hopefully that you can understand better some of the concept and application, some of the concept that I mentioned earlier, right? Right. I'm using fifth edition text from Professor Cheng and Roger. So in this example 4.1, it's mentioned about the experimental method, right? So in heat transfer or in engineering, normally we have three basic methods. First is experimental method. Second will be the analytical method. And the final one will be the approximation method or numerical method, right? The experimental methods means that you do measurement and then you get results, right? So most of the equation that we learn in engineering, they are based on observation, means that based on the measurement. And the second one will be analytical method, where the one when we derive the equation for temperature history for the lump system. That is analytical method. Since we know that the system is quasi-thermodynamic equilibrium, we are using energy balance. Right? Energy balance is a equation that you learn in thermodynamics, right? And then from that we can express the temperature history in terms of graph or in terms of equation, right? And the final one, using the computational fluid dynamics or heat transfer, you're using a numerical method, using a finite element method or finite volume method or finite difference method or other advanced numerical method. And this numerical method that you can use from some of the CAD application software like CATIA, they have all those method, right? They're embedded in the software so that you can use. So here we are looking at one census called thermocouples, right? We are using a specific geometry, right? Not thermocouple can have a different geometry because they serve a specific purpose. So what we're going to look at now actually is what they call it gas thermocouple. So we are using this gas thermocouple in order for us to measure temperature of gas stream. So we have a fluid in gas state, right? They are flowing. So you are using this type of gas thermocouple, and the temperature of the gas stream is to measure by a thermocouple, and the junction. Junction means the tip of the thermocouple, right? Is a name given to a thermocouple, and this junction allow a connection between two wires, right? Only thermocouple have two wires. You have to solder it with a specific method, something like that. Here we approximate that the junction have a spherical shape. and the diameter of that sphere is 1 millimeter. So this welded uh, parts has a metal property, right? So the thermal conductivity is 35 watt per meter degree Celsius, and the density is 8,500 kilogram per meter cube, and specific heat is 320 joule kilogram degree Celsius. And we assume throughout the process until it reach um, equilibrium with the surrounding fluid, right? The heat transfer coefficient does not change with time. So when you apply this topic, right? Um, we 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 also assume that the heat transfer coefficient does not change with time. So we want to know how long it takes. So when we talk about how long means time, right? So any problems, the heat transfer problems that has explicitly mentioned about duration or time. So this can be categorized into LAM system. There is a possibility that this problem can be considered a LAM system. So we need to determine as a engineering problem, right? To determine how long the thermocouple take, how long it take for the thermocouple to read 99% of the initial temperature difference. So here we look at the concept of what we call temperature difference, right? The solid temperature and the fluid temperature. But we are specifically indicate the state here, initial, you know, uh, before you place the thermocouple inside the gas stream. So that will be called initial temperature difference. Right. So the above is step. This from my experience. When we want to solve heat transfer approach, first we would like to identify whether the heat transfer system, right, is what is the temperature of the heat transfer system? Is the temperature varies with time, or both, or only change with space, right? So from that, we can identify whether the problem is steady or transient. Uh, Now, related to our current topic, if the problem is transient, we go for the simple method, right? We determine the Biot number. Um, and to determine the Biot number is quite tricky, right? Previously, I'll give you a quiz. You'll find that to get the Biot number is not straight, but it is on experience, right? So hopefully that we can look at what I mean by based on experience. Just to give some quick understanding, if we can compare the analytical method with the experimental method, right? So the experimental method will be the basis to help us to determine the correct Biot number, right? So this is a criteria. It will not be used in the calculation of the actual problem. It's just a criteria, right? Um, but when we want to calculate temperature history, we need to use the equation that we have earlier, right? But in certain cases, if we don't have a choice, then we can use the Biot number in the criteria of Biot number in the expression for time history.